All right. Let's get this done. Good afternoon. Have you got enough light back there? Have we got too much light here? No, you can follow it? Cool. Right. Today, second to last lecture is on pitch perception. And I'm going to try to introduce you to the basic concept of what pitch actually is. The quite interesting story on the physiological basis of pitch perception, so how we actually do it in our brain. That's what my research area actually is, so that's why I know about that, and that's why I try to teach that. Because it's a really good example of what we know, what the brain actually works, how the neural networks in our brain do pitch perception. It also has a lot of emphasis on musical perception, of course. I'm not going into musical theory. I think most of you are probably better than me in terms of music theory. But the basic of pitch perception is really relevant for that. The practical today is explore pitch in various stimuli. I've got a worksheet for you which asks you to create a number of stimuli yourself in Adobe Audition that all have the same pitch, allegedly, and to find out if that is the case and if you can order them in terms of their strength of pitch. Okay, let's talk about the definition. What actually is pitch? Definition Wikipedia is quite useful. Pitch represents the perceived fundamental frequency of the sound. It is one of the major auditory attributes of musical tones along with duration, loudness, timbre, and sound source location. So the most important things when we hear a sound are how loud is it, where does it come from, what does it sound like, and what pitch does it have. That's basically it. And if I order them in terms of evolutionary importance, it is where does it come from? That's the most important thing for us. And probably one that isn't here, namely how big was the sound source? That's a quite interesting concept, which isn't really described in the literature yet, but there is some research, groundbreaking research actually been done that goes to show that we're very, very good in discriminating the size of the source of sound, which evolutionary is very important for us. Think about evolutionary, where does it all come from? From fish underwater. How do they hear sound? They only really want to know two things, namely, can I eat this, or can they eat me, effectively? So are they small or are they big? A close relative to that, obviously, is the loudness of the sound, because large animals make louder sound. We're not talking about that very much here, therefore. But it's connected to timbre. Anyway, today we're talking about pitch. What is pitch? Pitch allows the construction of melodies. That's the most important thing about pitch. Pitches are compared as higher or lower and are quantified as frequencies. So if we talk about a pitch, a musical pitch, we measure it in hertz. It corresponds very nearly to the repetition rate of sound waves. That's what we're going to investigate in here. However, pitch is not an objective physical property, but a subjective psychophysical attribute. Right, pitch, although we measure it in hertz, that implies that we can measure it physically. We can measure it physically for a number of stimuli, but we cannot measure it for a whole range of other stimuli, where pitch becomes really subjective. I've got an example for you to listen to on Adobe Audition, where it becomes completely clear that you actually can't predict what pitch you hear, because everybody hears a different pitch of that sound. The official definition, there is an official standard industrial definition, is pitch is the auditory attribute of sound according to which sounds can be ordered on a scale from low to high. That says a lot, but I don't think it's a very good definition, because it just captures too many things. You can order something from low to high, also on quiet to loud. It depends on how you define low to high. So I don't like that definition. I like my own definition. It is the sensation of a sound which is associated with musical melodies. Everybody knows what a musical melody is, and I can play you musical melodies with 5 or 6 tones, and I can ask you, do you recognize the melody or not? And I can say, if you are able to recognize the melody, then it has a musical attribute, and that's what we call pitch, that musical attribute. But remember, pitch is not frequency. Although both are measured in hertz, they are definitely not the same thing. Frequency is what we measure in a physical device. Pitch is what we hear. It's a purely perceptual thing. And I hope at the end of this lecture it becomes clear to you what the difference between these two things are. Right, go to Blackboard, and because I still can't play any sound files here, I was promised that they might actually get some speakers in here. Go to Blackboard and find the shepherd's tone example, and listen to that for a second.
Shepherd's spiral.
Shepherd's pitch, shepherd tone. Shepherd's spiral, that's right. If you're interested, you can download it and look at it in Auditory edition. It's probably quite interesting to find out how that functions.
To me, is that half the slide?
Nobody.
Yeah, everyone's downloading the same file.
First one you can download it, yes, twice. Periodic lecture in the meantime. We can listen to it later. So what you hear is a auditory illusion, as you'll find out. You hear something which is physically impossible, which changes pitch all the time, but something is happening. So find out yourself how it works. We can discuss it later. It's quite interesting. What it demonstrates is that pitch is not a physical thing. It is a subjective thing that you hear, but not something connected necessarily with a one-to-one with the stimulus. Right. A simplest example for pitch is a pure tone. We had a lot of pure tones. You know what a pure tone is? Pure sine wave. That has one defined pitch, luckily. That's why it's quite useful for us, and we use that in broad measures for experiments and everything. But it's not very natural stimulus, obviously. We usually associate pitch with more complex stimuli like musical instruments or speech or other things that have a much clearer pitch than that. But it remains to say, many pitch sounds are periodic, and that's the key to most pitches, that they are periodic in their waveform. In which case, if a stimulus is periodic, this is a one-to-one law. If I repeat a stimulus 20 times a second, 20 is not necessarily, let's say, 200 times a second, you will hear a pitch of 200 hertz. That is fundamentally always the case. Okay. Let's go a little bit, 5 minutes into the physiology. Jump back to the basilar membrane. You remember that the basilar membrane was vibrating with the frequency of the stimulus. That thing here, remember, that's the organ of Corti with the hair cells, inner hair cells and outer hair cells. And these guys down here is the auditory nerve. And every time they flash yellow, that means there is an auditory action potential, a spike, traveling down the auditory pathway into the brain, and that is perceived as sound. Okay? So this thing vibrates as a function of the mechanical function of the sound, and this is translated into an electrical impulse down there. Now the point of that is that if we increase the stimulus amplitude, I think I talked about that already in terms of loudness perception. If we increase the stimulus loudness, so make a quiet sound to a loud sound, we get just more of these spikes. So this is the easiest, simplest example of neural coding. You just count the number of spikes that you perceive, and you know how loud a stimulus is. That also tells us about the frequency because we have the mapping of the auditory nerve on the basilar membrane. Remember, if we unroll the cochlea, we have the frequencies nicely arranged from the high frequencies here, 10,000 hertz, 1,000 hertz, 500 hertz, down to 20 hertz at the very end helicotrema of the basilar membrane. So that because we know that the neurons fire, the neurons are sitting all over at different places on the basilar membrane, we can come up with a coding scheme how auditory neurons code the frequency, and this is what's called place coding. Namely, you just have to know which neuron is associated to which frequency, and if that neuron is active, you know there must be 250 hertz in that stimulus. That's what's called place code, and that's a useful concept for the basic pitch perception when the pitch is associated to the frequencies. Slightly more interesting is a completely different way of coding frequencies, which is in the temporal domain. What we can do if you look at one of these hair cells and you fix it, and you see the stereocilia vibrating, and you fix the waveform of the stimulus, and it goes in with one cycle. So we've got a periodic waveform here, pure tone, and the hair cell fluctuates exactly once per period in the motion of the fluid. And this little dot here describes the time, and we look at it as a function of period. So this is an infinite wave, obviously. If we look when the neurons fire, namely every time these nerve cells here become yellow, just as in this picture, and we plot the histogram of that. So every time they fire, you build a little bit of an histogram up over time of how many spikes have been fired as a function of time. If you do that long enough, you see that you end up with the representation, which is a little bit rough, but it is a copy of the waveform. So what the auditory nerves are doing, with the simple way that they can communicate, the only thing that they can do is spike or no spike, if you like, a 0 or a 1, is they digitize the waveform. So because at the time you know when they are, but if you know when they are firing, in terms of the in relation to the waveform, to the periodicity of the waveform, they will produce a copy of the waveform to the amount that they can do that. What they cannot do is code the negative half wave of the wave, of the sound, because they can only either fire or not fire. They cannot negative fire, if you like, so they can only produce positive half waves. And they will produce, a nice representation of that. If you wait long enough, well, the longer you wait and the more nerve cells you have, the better representation of sound you have. So that is, if you say that is digitized, that's not a bad way to put that, because you get it from an analog signal now into a digital signal, because you can either have spikes or not spikes. But the point is, the spikes will always be coupled to the waveform. And so if you plot that as a function, as a long function of the sine wave, then the intervals between that spike and the next spike will be exactly one period of the waveform. And that's what's important, because if you have the periodicity, that's what's called phase locking, first of all, because the spikes lock to the phase of the stimulus. They always produce a spike at the same phase. And if you do that for a longer time, and you measure the periods in between these spikes, or the times in between them, then there will be, the neurons might not be fast enough to fire every period, especially for higher frequencies, but if they fire, they will always be multiples of one period. And as you know, time and frequency are just two ways of looking at the same thing. If you know what the period between two intervals is, you know the frequency of the sound. It's 1 over the interval. Now this face locking is something that all auditory nerve fibers do. Here it is measured in terms of how well they face lock. So this axis here, y-axis, is giving a measure of how well auditory neurons do tend to fire with the same face. And if that was 1, then they would be firing exactly perfect. At 0, they're firing completely randomly. That's what the synchronization index is. And you see these are data for a cat and for a guinea pig. The cat is better than the guinea pig. The human is pretty much between the cat and the guinea pig. If you have a barn owl, it would be even better. But you see, the point is, there is an end of this face locking. So you're very well at 1 kilohertz, 2 kilohertz, 3 kilohertz, it completely breaks down. So above 3 kilohertz, you do not have the ability, your neurons are not able to follow the waveform on a cycle-by-cycle basis anymore. That's an interesting frequency, because this is the end of our musical pitch perception. If you have a piano, what's the highest note on a piano? You musicians? C. What frequency? I don't understand these C things. I think it's a C dash 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 dash. But what frequency is it? It's around 3,500 hertz. And even that is actually so high that it doesn't carry much musical information anymore. And above that, it's pointless, because you do hear that there is a pitch, and you can say that's higher or lower, but you wouldn't make music with it. And the reason for that is here in this picture, because your nerve cells are not fast enough to fire more than 3,000 times a second effectively, or coupled to the waveform at least. I say here 5 kilohertz, that's a little bit optimistic. It's different between people, it's certainly different between various animals. A cat is better than a human, it's better than the guinea pig, and we're all much worse than the barn owl, because barn owls are specialists for that. They have developed to be able to do that up to 10 kilohertz. So they would have a complete higher octave on the piano if they would play piano. Okay. One thing, because it is interesting to notice here, is that we have more than one neuron. And there's a reason for that, because neurons are not fast in themselves. So we've got 8 neurons here, or nerve fibers. And you see, this is a waveform, and the time is illustrated here. And these things there are spikes. So each of these fibers will fire at a certain time during the stimulus, usually when this is at the top. That's the face locking thing. But they are not fast enough, each individually, to fire every single period. But point is, you've got more than one of these. In fact, we've got about 30,000 of these. And if you add them all up, you get a really nice representation of the waveform again. You see that the distance, the difference between each spike is exactly the difference between the period of the waveform. Now that gives us reason to believe, all of that evidence here now, that we actually perceive musical pitches by measuring the time intervals between spikes, which is the same as measuring the time interval between 2 periods of the stimulus. That's why every stimulus that has a periodicity also has a pitch. Okay, just to finish that, neurons share the workload. This is a sentence. What is it? Joe took father's green shoe bench out. And 1, 2, 3, 4, 5, 6, 7, 8 completely different neurons that are independently measured as how they respond to that sentence in a guinea pig, I hope. And this is the spectrogram of the same sentence. And you see that the neurons, again, give a pretty nice representation. So each individually doesn't do very much to speech perception, but if you look at all of them together, then you see that they resemble quite a lot the spectrogram. So where the neurons fire, there's a lot of energy in the signal. So up there, up to the point that if you have a transition like this transition in here, where you have a frequency glide from 1,000 hertz to 3,000 hertz, this is represented in the neural firing. So that's a really nice representation of how neurons together, you've got thousands of them in the end, not only these 9, share the workload in order to, if you like, digitize the waveform. That doesn't mean there's any kind of perception involved in that. So far it's only a representation of sound, but once you've got the sound represented in the brain, it is much easier to analyze it, obviously. All right. Okay. That's my favorite slide, but unfortunately I can't play you these examples. Did anybody actually get the Shepherd scale there?
No, that wasn't.
No. Do these work down here? Did anybody listen to them yourself from the lecture? So what they do is, this, as a repeat, we perceive periodic sounds as having a pitch. This is the demonstration of that. This is 10 clicks a second. So one click sounds like a click. And I'm now doing, slavishly, just repeating that, namely 10 times a second, 10 clicks. It sounds like click, 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 and you can consciously, almost, if you're trained, you can consciously follow these. It's a bit difficult to count them. 5 you could easily count, 10 you can't count, but you hear each individual click as an event. Does it work? Good. So listen to the 10, and you can tell me that sounds like click, 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 click. Okay? Boring. Now what I do here, obviously, is I increase that, 20, 40, 80, I always double that. 20 hertz you will have trouble to follow, but you still hear individual clicks. At 40 hertz, something new happens, because you are not fast enough anymore to follow each individual click. That's what is, in technical terms, in the literature is called a motorboat perception, because it sounds a bit rough. It's very, very rough stimulus. It hasn't got a pitch, but you can't hear individual clicks in there anymore. It's just too fast. So what's happening here is the equivalent of a film. If you see one picture, you see one standing picture. If I show you 20 standing pictures per second, you start perceiving it as a film. You don't see the individual pictures anymore, as you know from television, but you see the film. You don't even care that there are individual pictures anymore. Now here, the same thing happens. At 40 hertz, you don't hear individual clicks anymore, but you hear a general concept, a general perception. And at 80 hertz, everybody will agree with me, is where a pitch starts kicking in suddenly. Well, more or less suddenly. The perception that changes happens somewhere between 40 and 80 hertz. But at 80 hertz, certainly 160, it should be really, really, really obvious that there is a musical pitch now. Now, the logic, what's happening here, is the explanation is that our neurons can't fire fast enough that we perceive them all in one go. But the point is that we don't have to. This is an ingenious mechanism of reducing information, if you like. Because I don't get any more information from the 79th or the 80th click per second, but I can substitute the whole perception by one perception or one number, namely 80 hertz. And that's what I hear. And I hear 160, 320, 640, and they have a very clear and distinct pitch for me. And I can certainly not count 640 clicks, but I can start making music with them. And this is where pitch comes in. Pitch is an ingenious way of our brain to reduce the complexity of the outside world. In fact, 90% of what the brain is doing is protecting us from the complexity of the outside world. If I would see everything that is here and hear everything that is there, I would go crazy. But what I actually what I'm able to digest, you might have read these numbers, is something like 5 to 10 bits per second. So 1 bit is not very much, it's a decision between yes and no. 10 bits per second is what I can consciously work on. And counting 640 clicks per second is much, much, much too fast for me to actually work on that. So I reduce it, or my brain, for me, transforms the 640 things into one perception, one number, 640, and just presents me with that number. And that's why pitch is so useful, because it's a very, very efficient way of reducing information. Okay, here are some examples, again, for the connection between pitch, or the waveform, and the spectrum, to make totally clear that you can have different waveforms. So you have a pure tone, you have a rectangular wave, you've got the click train that we just listened to, which have completely different spectra, but these have all the same pitch for us, because they all have the same period. So they all have these, I think, 1000 hertz tones. you've got 1 millisecond between these two clicks, 1 millisecond between two rectangles, 1 millisecond between two sine waves. They sound completely different, but they have the same pitch. And the frequencies, the best way to say what a frequency is in the spectrogram. That's all the frequencies in the sound. They are different. That's why they sound different. Now the pure tone is a special case because it only has one frequency. That's why it's useful in the Fourier transformation. The square wave, if you do the FFT, it comes up with all of the odd number harmonics, so 1, 3, 5, 7, 9. And the click train has all the harmonics, so 1, 2, 3, 4, 5, 6, 7, up to infinity, but a lot of them. Okay? So they all have different spectra, and that means they have a different sound, a different chroma, or a different... well, they sound different to us. But again, the pitch is the same. Right. Here are for, just as illustration, you've got the spectrum of other sounds as well. One single pulse is a broadband noise. The white noise, obviously, have a straight spectrum, and a short tone would become wider and wider. These are similarly, they don't have a pitch perception because they don't repeat, none of them. So they wouldn't have a pitch. Okay. So the aspects of a sound that lead to a musical perception is called pitch, and everything else, namely everything in the spectrum, is called timbre. So you have sounds with the same pitch can have different timbre. That's the case in an orchestra. You've got a violin and a trumpet, those both playing an A. They have the same pitch but different timbre. You can have the same thing. You can have the same timbre but different pitches. If you play with a violin two different notes, they have the same timbre. They sound similar, but they have a different pitch. So these are the two independent components of a perception, if you like, pitch and timbre. The frequency has nothing to do with it. Frequency is just a description of the physical sound, whereas pitch and timbre are a perceptual description of it. Okay. 5 minutes about modeling. How do we understand how our brain actually makes sense out of that? And I already said that we have two different kinds of perceptions. One is through the time, it's called temporal pitch, and one through the place on the basilar membrane. That's the place pitch. And there are two different ways that neurons code the frequencies. And let me introduce you to, in the real world, if we have a pulse train, how we understand how the brain actually makes sense out of that pitch. And this is quite interesting because it has a number of concepts that are necessary for that. First of all, first line here are the frequencies of our pulse train. Okay, we already saw the spectrum. So this are the frequencies 100, 200, 300, 400, 500 hertz. So that would be a pulse train which has exactly 10 millisecond repetition rate. That would be the spectrum, 10 millisecond equivalent to 100 hertz. Now, we spoke about auditory filters a lot. You probably measured your own ones relatively precisely yesterday or Thursday, Tuesday. They are more complex than that, but for our modeling purposes, these are good enough. They are a bit rough, but it's easy to model, so we just assume that they are good enough for us. And what we know is that at low frequencies, they are much sharper than at high frequencies. That's because the basilar membrane has a logarithmic frequency spacing. This is a linear frequency spacing up here. So if we plot our filters on a linear axis, then they will become much broader to the end. Now what happens if you look at a spectrum through these individual filters and add them up? That's what the basilar membrane is doing. It consists of a number of arrays of filters, third octave wide filters. That's what we talked about on Tuesday. And in the end, it just moves up and down, and that's what we call excitation pattern. So they move up and down, and this is basically the envelope of this up and down movement. Now, for the low frequencies, let's say this one here, 100 hertz, there is a specific filter that is so narrow that it only lets through 100 hertz. And then on the excitation pattern, you get this, what's called then a resolved harmonic, because you only have one filter in which this one component is active. If you go to higher frequencies, the filters become wider, and there are so many frequencies now going through that filter that they are not resolved anymore. They all just mix up, and you don't see a difference between, well, 2500, 2600, because they're all in the same filter. Now these resolved and these unresolved harmonics are the key to pitch perception, because we use them both. Only together they explain our perception of pitch. And I try to explain that with few examples. What we need for that is we need to look at the movement on the basilar membrane. So if you just look at, as a function of time, how the basilar membrane moves at low frequencies, it just fluctuates with the frequency. And at higher frequencies, it fluctuates faster, because every part of the basilar membrane just resonates. But because we've got all frequencies in there, all parts of the basilar membrane will vibrate. But if you go to high frequencies, here 2000, 3000 Hertz, you see that the basilar membrane will go with what's called the fine structure very, very fast, but it will also be modulated in envelope slowly. And the modulation is because of the stimulus repetition rate. So the modulation will capture exactly the repetition. The fine structure is sort of irrelevant, because it only captures where on the basilar membrane you are. Just as a curly bracket, if you like, this is exactly what we do with cochlear implants. You know, cochlear implants, electrodes in the inner ear, and they stimulate electrically the nerves directly. And what they do is they completely ignore the fine structure, just take the envelope. We do we measure with the filter bank the sounds into different frequency channels, take the envelope information, and just send electric clicks at the maximum of the amplitude. That's all that a cochlear implant is doing. And you get the speech perception from that already. Okay, but that's not the point here. The point is for our pitch perception. Now, with that knowledge of the basilar membrane, we can understand what these two place codes and temporal codes are. Let's say we have, as an example, you want to discriminate 500 Hertz from 550 Hertz. That's easy. You should know that by now. It's 10%. Your JMD is something like 1%. You can easily hear the difference between these sounds. And you can either interpret that as being in the rate code. That would be the basilar membrane vibrating up and down, and that's the envelope. For 500 Hertz, it's the left one, and for 550, it's the right one. And you see that there's a slightly different place. So the place code means you know that you're either listening to that place or to the right place. That's not very precise, and I don't believe this is actually how it works, but in theory that would be possible. What I believe is at this frequency much more relevant is that the difference between the temporal codes, so as I said, the spikes, is here the spikes are 2 milliseconds apart, and here the spikes are 1.8 milliseconds apart, or multiples. But you can hear the difference between 1.8 and 2 milliseconds, and that gives you the difference between these two pitches. Okay. Right. How do we translate that into a model, what we can imagine? The simple way is to think about what's called template matching. And let's say you have a built-in, probably learned template in your brain that's like looking at a picture and see, yeah, that's a square. And sometimes you must have learned in your life that a square is something with 4 corners. But you actually only need to know that once, and you can look at any other square in the world and identify it as a square because it has 4 corners. Similar thing as you can do with pitch. You can have a template which has 100 Hertz spacing, or you can have a different 100 Hertz template, 110 Hertz template, where the spacing is 110 Hertz. Now, if you have a sound now, let's say this might be a spectrum of some sound, 100 multiples of 100 Hertz, 200, 300, 400 Hertz, and you put these two templates over it. The 100 Hertz template fits it nicely. At the 110 Hertz fits that one nicely, but these ones don't fit so well. So that's what's called template model. That would have been learned, but it would explain, if you just see what the basilar membrane is doing, how our brain could make sense out of that, and to discriminate, or to find out that this sound actually was 100 Hertz and not 110 Hertz. If you think about these templates, obviously you can, for example, double these frequencies. So instead of 200, 300, 400, it would have 400, 600, 800. Musically, that would be the octave. And it would fit perfectly in the same template. Most people assume that this is the reason why octaves are so similar to each other. They're the same tone. They just differ one octave apart, so different in pitch, but the same tone. If you think about it in terms of these templates, the same template fits all octaves. And it also fits other simple musical, what are they called, relationships, like fifth or seconds or something. And this is what's usually generally be assumed in modeling quarters to be the reason why musical pitches are actually for us to be harmonic or not harmonic. Because the harmonic ones fit the template, the non-harmonic ones don't fit the template. Okay, the drawback is templates must be learned. That's an interesting thing. You cannot imagine a neural network that comes genetically, because it would be much, much, much too complicated, that can have all of these templates built in. And, well, we can phrase that as a question. Is there a time when babies cannot hear musical tones? And these experiments are actually done, and it seems that there is indeed a time when babies have to learn these. You need to understand, you need to learn what an octave is, even if you don't learn it consciously. You hear it by listening to sounds, you hear what an octave is, and you develop the templates for that. Templates don't work everywhere. They only work at low frequencies where you have these resolved harmonics, because if you don't have resolved harmonics, these templates don't work, obviously. And they fail to explain pitch perception at higher frequencies, or where there are no resolved harmonics. For that, we need the other theory, namely the temporal models, time. And here we illustrate this 10 millisecond click train again, 100 hertz, 10 milliseconds. What we know on the basilar membrane, is just a repeat, we have the high frequencies and low frequencies. They all vibrate somehow as in the response to this click train. And the auditory spikes, they just would look like that. This one here would fire there, there, and there. This would fire at each of these peaks, and here it starts more with the envelope. This looks completely random, and indeed if you look at one, that might be completely random, but if you look at them all at the same time, then you see that there's a general interval between there and there, which is dominant in all of them, which is exactly the repetition rate of the sound. That is more generally assumed to be the model how pitch perception, musical pitch perception work. So there's an effective way of extracting periodicity or pitch, measure the time interval between the periods. That can explain the pitch perception in most stimuli, but not all. Neural mechanism out of correlation. The interesting issue with that is, although everybody believes that this is the case how we actually hear pitch, there is no neural physiological evidence that we actually do. Although there are millions of dollars spent and hundreds and thousands of people are looking at that in psychophysics and in physiology, but it is not clear that neurons really do that. It is quite obvious that it would be the best way to do it, but that doesn't mean that the brain actually works like that. So the exact mechanism isn't clear today, but it is clear it must be some kind of combination between the template model, so looking at specific areas where frequencies are, and the temporal model, so measuring the time interval. Okay, that's just a summary. The only thing here worth mentioning is there is, for place code and time code, there are good examples for both of these stimulus. That's why I showed them before. The place code, a good example for which stimulus explains that, is a sine wave. The pitch, it is an ideal example for a place code because it only has one place on the basilar membrane where it is active. Whereas the click train stimulates the whole basilar membrane, so you cannot make sense of the template there, but you can make perfect sense of the intervals between the periods, and that's why it's a good example for the time code. Okay, that was my lecture on pitch. There's a whole lot of stuff in there, and I want you in the exercise to create stimuli yourself that have the same pitch. That's what's basically there's a lot of text for you to read, and you start with producing a pure tone of 250 Hertz. So all the stimuli on here, and if you really struggle, because these ones are all easy to produce, so I ask you really to produce them, but if you really struggle, they are on Blackboard as well. So all of these stimuli, and there are 10 of them, are sounding completely different, but they all ought to have the same pitch of 250 Hertz. I want you to find out if that is the case, and explain to me, or think about it. Do you think that it's rather the template model, so the place code, or is it the temporal model, the repetition rate, that is responsible for your perception of this 250 Hertz? And some of them work with one, and some of them work with the other. Okay. And we just make a short break, as usual. And you can also carry on doing your measurements from Tuesday if you want to, when you finish there. And I'm here to help with everything. Can you help me?
Huh? I just wait.